Alright, so this is the last little bit of electrochem. Kind of flown through this, but hopefully some of it will stick. An electrolytic cell, remember, this is the kind of the reverse of your voltaic cell. It's using an outside source to move the electrons in the unfavorable direction. So what was a non-spontaneous reaction, now we're kind of forcing it in the opposite direction. So it kind of resets the original reaction. So in a voltaic cell, the anode is the source of electrons. In an electrolytic cell, it still is, but the electrons are being pulled from the anode by an outside source and pushed to the cathode. So the way to think about this, and try not to get too confused with it, is what used to be the anode is now the cathode. So on a voltaic cell, what was the anode is the cathode on an electrolytic cell. What was the cathode on a voltaic cell is now the anode in an electrolytic cell, and we're forcing them in the other direction, forcing the electrons. That's what I mean by them. So the power source drives electrons toward the cathode, so the anode has to be connected to the positive terminal of the battery. The battery is what's forcing this in the other direction. The cathode must be connected to the negative terminal of the battery. So in order for this to work, the battery that you're using has to have more potential, more power than the original cell. So if you don't have a strong enough battery, it's not going to push the reaction in the opposite direction. You have to have a strong enough battery. That's just kind of a summary of everything that I said. In predicting products of electrolysis, there's a couple of things to remember. If you have a molten salt, so remember salts, they won't conduct electricity if they're in the solid form. We have to dissolve them, but another way to do that is to melt them down. So molten salts would also work that way because now the charged particles, the ions, can flow freely. So in that case, the anion is oxidized, the cation is reduced. If you have a mixture of cations and ions and you are trying to figure out what's going to happen, you just look at your little reduction potential chart, and the cation that is most easily reduced will be reduced first. The anion that's most easily oxidized will be oxidized first. I mean, you probably could have already put that together. One thing you definitely need to remember, though, that there are some metals that are not easily reduced. So if you tried to reduce them and they're in aqueous solutions, it wouldn't work because you would end up just reducing water, because water would actually reduce at a lower voltage than those metals. So you got to keep that in mind. Last thing here is stoichiometry. So with electrolytic cells, we're supplying current, we're forcing in the other direction. We can use this to like electroplate stuff. And so a lot of cool things can happen, a lot of cool problems we can work using stoichiometry because of what we know about current. 1 amp, this is when we're talking about current, is 1 coulomb per second. But we also know that there's 96,485 coulombs per 1 mole of electrons. So if we have our balanced equation that shows us here that with 2 moles of electrons we can get 1 mole of solid copper, we can actually, since this is a unit of time, we can figure out how much time it takes to put a certain amount of, or to plate out a certain number of grams of a metal. And it's pretty nifty. So remember your conversion. So if we had, like, let's say grams of copper and we want to figure out how many seconds it took us to do that, we'd have like grams of copper, then we'd put the molar mass of copper, which is 63.5 grams 1 mole. Then, according to our balanced equation, 1 mole of copper takes 2 moles of electrons. Then we know that 1 mole of electrons is 96,485 coulombs. Then an amp, so let's say that we have a flow of like 3 amps. So 3 amps is equal to 3 coulombs per 1 second. So 3 coulombs in 1 second. And now you can leave it in seconds, or you could take it to minutes. So however much copper you want to plate out, let's say we want 100 grams of copper, that will tell me how long it would take with 3 amps of current to plate out 100 grams of copper. So it's a pretty nifty thing. Last thing is undesirable redox rings. So we're talking about rust, corrosion. A couple things to know. Moisture has to be present for rusting to occur. You need the ions to be able to flow freely. So moisture helps that. Additional electrolytes also promote rusting by enhancing current flow. So cars are going to rust more quickly in areas that are cold or near the coast. Now, what I mean by cold is if it snows, then they put down salt on the roads and whatnot. So now you got moisture from the snow, but you also got electrolytes from the salt. So a lot of places like, the Dakotas or Michigan or somewhere where they're getting a lot of snow, you're going to have cars that rust more quickly. And then, of course, near the coast, you have salt water from the ocean that could do the same thing. Also, presence of acids promote rusting. That's pretty self-explanatory. Those are also ions. So I think that is all we got. So hopefully that helped.